Welcome. Today we shall look into some of the examples of the microscopic balances. So, in this particular lecture, what we shall be looking into that how we can apply the model equations for the heat exchanger. Now, here we have a case of heat transfer using a double pipe heat exchanger. Before I start with the problem, let us first understand what we mean by heat exchanger. Heat exchanger is a device which is used to cool or heat up a fluid using another fluid. The fluid which is to be heated up or cooled down is the main fluid which is going to be used in the process or is already in the use in a process. So, this fluid is called the process fluid, and the fluid which is there to help in the heating or cooling of the process fluid is called the utility fluid. So, we have two types of fluids here. For example, if we have say water which is to be heated up. So, to heat up the water we may use some other hotter water or steam or some other kind of fluid. So, this cold water will be considered the process fluid and the other water will be considered the utility fluid. Okay? So, now these fluids may be gas or may be liquid. So, in the industries you will find that at various places we are many times doing this heating or cooling very frequently, and everywhere you will find that there are heat exchangers being used. We do heat exchange also at our home in a different manner, and there are various kind of configurations of this heat exchange. Now, let us take some example from our home. Many times you have found that you are trying to cool down say hot milk or say hot tea or some hot water, and what you do for that is that you take a glass of the hot milk or hot water and you dip this glass in a bowl which is containing some tap water which is at a lower temperature than the hotter milk or the hotter water. So, in this way you find that through the wall of the glass heat is exchanged, and due to which you will find that the hotter liquid gets cooled down. At the same time you find that the liquid, that is the tap water which was there initially in the bowl, is also getting a bit warmed up. So, that way you see that there is a heat exchange between the two liquids and you are able to get the cooling of the hotter milk or the hotter water. So, in this case you can see the hotter milk or the hotter water is the process fluid, and the tap water which was used to cool down is the utility fluid. Another way you can see that many times we try to cool down the hot water which we get from the geyser to take shower. Now, in that case what you do, you mix up the water from the tap directly into the hot water obtained from the geyser and you try to cool it down. Now, in this case you see that again you are getting some cooling, but now you get some mixing also. And in this case the geyser water is the process fluid and the utility fluid is the water from the tap. But in this case the heat exchange is occurring by the direct contact between these two fluids. Okay? So, in this way you see that we are having two types of heat exchange. One is the indirect cooling, that is the first example I gave you, and the second one is the direct cooling, the second example I gave you. So, this is two configurations. Then there could be in the industries you will find that only one contact may not be sufficient. You need to have sufficient contact to cool down or heat up a particular process fluid. So, in that case you need some more contact time, or sometimes you need to give more space to get this kind of cooling or heating. So, you will find that in the industrial applications there are various types of heat exchangers possible, and moreover the more and more work are being done on this heat exchanger innovations. Why? Because we are trying also to reduce the size of the equipment so that we can get some advantage in terms of the capital cost, also in terms of the operational and maintenance cost of the equipment. So, this kind of research work is going on so that we can also bring down the size. Okay. So, in the industries today you will find that there are some conventional heat exchangers and there are some non-conventional heat exchangers. Now, the double pipe heat exchangers which we are talking about in this particular problem is belonging to the conventional type of heat exchanger. Now, in the double pipe, the name signifies that there are two pipes and these two pipes are containing the two fluids. So, let me first tell you how these two look like. So, let us say there is a pipe of some diameter and into this pipe we put another pipe of smaller diameter. Okay, so these are two pipes. So, I can say this is another pipe. Okay, and these two pipes are generally put in a coaxial manner so that they have the same axis. My drawing is not showing that same axis, but it is generally put coaxially. Okay, so the axis. So, along this axis, this is symmetric, you can see. Now, you see that in these two pipes, you are having two fluids. So, suppose I am putting fluid 1 over here, okay, and this is the annular space between the inner pipe and the outer pipe, and the other fluid may be going through this, the inner tube. Okay. Now, you see that again in this case there could be variations in the configurations. I can put this particular fluid in the same direction as the outer fluid, or I can also put it in this direction. Okay. Now, if it is in this direction, then we call them parallel flow. This is called parallel flow heat exchanger. And in this case, if we are talking of these two, then in this case we have what we call the counter current flow. This parallel flow is also sometimes called the co-current flow. So, co-current and counter current. Of course, counter current is also parallel to these two. So, it is better to call them co-current and counter current. Other than these two configurations, there could be configuration where you find that the outer fluid is coming like this. That is, it is coming at a 90-degree angle to the inner fluid. So, in this case, suppose I talk of this one or this one, both of these will be called the cross flow. So, we have these various configurations in a heat exchangers. Okay. Now, with these various configurations, we also have some other configuration in the sense that we may have multiple number of the inner tubes, okay, and only one outer tube and multiple number of inner tubes. In that case, we call it a shell and tube heat exchanger. Okay. So, I will show you a few diagrams of the shell and tube and these other heat exchangers shortly. So, whatever it is, we understand this that these heat exchangers can have different configurations and the choice of the configuration would depend on the objective, that how much heat we need to take out or we need to give in, and there are many other considerations in terms of the pressure drop in the heat exchanger, in terms of the size of the heat exchanger also changes with a change in the configuration of the flow of these two fluids. So, there are various considerations need to be taken into account to decide the type of the heat exchanger to be used, and these issues are covered separately in dedicated courses on heat exchanger and heat transfer. So, I will not be going into the detail of those issues in this lecture. So, here we have the heat transfer using a double pipe heat exchanger. A liquid stream is heated by the condensation of steam at constant temperature Ts. Now, you see that here the colder liquid is to be heated up using steam, and here we are saying the steam is at a constant temperature. Now when can that happen? Generally you know, whenever the heat is being transferred from a given fluid, the fluid is supposed to get cooled down. But when we are talking of a saturated vapor, then you see that if the saturated vapor is being condensed and it is going to a saturated liquid state, then during this process what we find that the temperature would remain constant if the vapor is of a pure component. Okay? So steam, when it condenses to saturated water, it will be releasing the latent heat of vaporization, which is quite substantial, and that will be enough to heat up a colder liquid. Okay? So this is why we are saying that the steam is at a constant temperature Ts. On the other hand, you see that if in reality you find that after the condensation, the condensed water may also get subcooled from the saturated state to the subcooled state at the given pressure. In that case also you can say that some amount of heat would be released, and this heat will be coming from the sensible heat transfer from the saturated water to the subcooled water. However, you will find that generally for some finite or reasonable temperature difference, you see that the contribution of the latent heat of vaporization is generally much more than the sensible heat contribution, and that is why you see that we many a times neglect the contribution of the sensible heat in comparison with the latent heat of vaporization, unless otherwise we have a very large delta T. Okay? So in this problem we are assuming that the subcooling effect is negligible in comparison to the effect of the condensation of the saturated vapor of the steam. Now the liquid enters in the inner tube at a temperature of TL in, and it is going out at a temperature of TL out. Okay? And we are demarcating the inlet and outlet of the inner tube with this Z. The Z signifies the direction of the flow. At the inlet it has having a value of giving a value of 0, and at the outlet we are giving it a value of L. That means the length of the inner tube is L. Heat transfer from the steam to the liquid involves heat transfer resistances from steam and the wall of the inner pipe and between the wall and the liquid. Now you see that whenever there is some heat transfer occurring, there will be some resistance to heat transfer. Now when you talk of if I draw here the inner tube first, okay, and then what I draw with this, I draw the pipe. This is suppose is a pipe, the pipe wall. So I am drawing on one side, the same thing will be repeated on the lower side also, and here I am drawing the outer tube. Okay, and outer tube will also have some thickness, wall thickness. Okay, so here we can also put one wall thickness over here. This shaded portion is the wall. Now you see that now we are considering only the heat transfer between the outer tube and the inner tube. So we are neglecting the heat transfer over here. So we are not concerned with that heat transfer. So we are not concerned with the wall of the outer tube. Now when the heat is getting transferred, so let me put with some other color. So when the heat is getting transferred from here to here, it is encountering three resistances. One resistance will be within this steam. So this is steam and this is the liquid. So we shall be having three resistances. One resistance will be within the steam. Okay? One resistance will be within the wall of the inner tube, and another resistance will be within the liquid. Now you see that in the steam and in the liquid we neglect generally we have three types of heat transfer. One is conduction, convection and radiation. So for any kind of fluid, generally the fluids have very low conductivity. So in case of steam and liquid, we neglect the conductive contribution. we talk of the convective contribution. Moreover, for the radiative heat transfer to be appreciable, we need to have very large temperature difference, because you know that for the radiative heat flux, the heat transfer depends on the T raised to the power 4. Okay? And you can easily figure out that this radiative heat transfer will be effective only when the delta T is quite large. Okay? So, we are also neglecting the contribution of radiative heat transfer for the kind of applications we are talking about. Okay? But this is not a mandatory assumption. You have to first check the difference between the temperatures of the hotter and the colder fluid. Based on that only you should account for or neglect the contribution of the radiative heat transfer. Now you see that for the steam and the liquid, we are going to consider only the convective heat transfer, so that there are only convective resistances within the steam and in the liquid. On the other hand, for any kind of solid, there is no contribution of the convective heat transfer. So, it is only the conductive heat transfer, and as I have just said that we are neglecting the radiative contribution. So, for the conductive heat transfer to be appreciable, we have to have a high thermal conductivity of the particular solid. So, many times we assume that the thermal conductivity of the solid is quite high, so that within the wall of the tube there would not be any resistance due to the conduction. So, that what it means is this, that within the wall of the tube there will not be any temperature gradient. Okay? The wall temperature will be constant throughout the thickness of the wall, and this kind of assumption does not incorporate much of error in the final result. And also we have to understand that we choose the material of construction of these tubes in such a manner that the wall has very low resistance, because we want the heat exchange to be effective. If the wall also offers a large resistance to heat transfer, then what we would land up with? We would land up with a bigger heat exchanger. So, from that point also we have to see to it that the material of construction of the tube wall should be such that it does not offer any kind of resistance to heat transfer. So, with these considerations we can neglect the heat transfer resistance in the wall of the tube. So, now that is why we are saying that the resistances are lying from the steam to the wall and then from the wall to the liquid, that is within the steam and the liquid. And now we have been asked to establish the balance equations to determine the temperature profiles in the flowing liquid and the wall of the inner pipe. Now you see that due to the heat transfer, the wall of the tube will be having a gradient of temperature not in the radial direction but in the axial direction, because these two fluids, the steam and the inner liquid, both of them are exchanging the heat, and also due to which this wall is the medium, so wall is also getting affected. So, there will be a gradient of the temperature in the wall in the axial direction. Okay? So, with this now we go to set up the model equation. Now, you see that because we have been asked to find out the temperature gradient, we will be looking into the energy balance equation. Before this, let me just put you how a typical double tube or double pipe heat exchanger look like. It is sometimes called double pipe heat exchanger, or sometimes it is also called tube in tube heat exchanger. So, you can see that there are in this particular thing, it is a outside, from outside how it looks like. You see that there is a tube inside, this one is showing inner tube and this outer one is here, and there is the inlet of the outer tube. Okay? So, the liquid, you can say, it will come through this tube which is going like this. Okay? So, we call it passes. So, this is one pass, this is second pass, this is third pass, this is fourth pass, fifth pass and sixth pass. So, there are 6 passes of the inner liquid in this case, and this is the flow of the steam. The steam will come like this, okay, and it will come like this, it will come like this, it will come like this. So, steam is flowing like this. So, in case of steam also you find there are various passes. This is one pass, this second pass, then third pass, fourth pass, fifth pass and sixth pass. So, there are passes, and these passes are made why? Because we do not want to have a very long pipelines. If we do not put passes, then we will end up with some so long pipeline that by calculation it may come to kilometers even. Okay, that is unreasonable. Okay. So, we have to put a design in such a manner that we can make it very compact in a reasonable size, and that is why we, to give more contact time between the two fluids, we make passes. So, this is a tube and tube configuration, and as I told you, there could be shell and tube. In the shell and tube, it is something like tube and tube. Only thing is this, the number of inner tubes are now increasing, and the outer tube you can say that is the shell. So, here you can see that from one side the tube side liquid is moving through these shell these tubes, and here you see that the shell side fluid is flowing and it is coming out like this. And here you can see the baffles are being put. The baffles have various reasons. One is to hold the tubes in the places, and also to see to it that these baffles also kind of affect the heat transfer between the two fluids. Okay. So, I am not again going into detail of the baffles, because the baffles have various types of designs also. So, that is not under the purview of this particular course. Okay. And these tubes are held at the two sides with some tube sheets. Okay. And so, you can see that the steam you can imagine that steam is going like this, and the liquid is going like this. Now, you here see here that overall it looks that as if the hotter fluid is say coming from this shell fluid is coming from this side and going out this side, and the tube side is going from this side and coming out this side. So, overall it looks like a counter current flow. But if you look inside, you can see that here this tube is going like this and the fluid is passing like this. So, if you follow this particular path, you can see this is something like a cross flow. So, overall it is counter current flow, but within this you can see something like a cross flow happening. Okay. And this is we call it one pass on the shell side and one pass on the tube side. We may have multiple passes on the both the sides. So, here you can see a configuration where the tube side thing is passing through this the tubes, and it is taking a U-turn and going through these tubes. So, there are two passes on the tube side. One is this pass and this is the second pass. So, there are two passes on the tube side. On the shell side, we have only one pass, and it is also, you can see, it's a cross flow. And here in this configuration, you can see that the tube side fluid is going from here. It is first going like this, okay, and first pass, then it is taking U-turn, this second pass, then taking a third turn, it's a third pass, and then it's going like this, it's a fourth pass. So, there are four passes on the tube side. On the other hand, when you look at the shell side, you can see the shell side fluid is flowing like this, it is moving like this, and of course, it is moving like this, it is taking a configuration like this is a configuration, and then it is taking a second turn over here. That means, this is one pass for the shell side, it is taking second turn over here, again it is moving like this from here, like this it is moving and is going out. So, you can see here that we have two passes on the shell side and four passes on the tube side. So, this is how we count the passes on the shell and tube heat exchangers, though these are some just examples to give you some feeling how these heat exchangers work. Coming to our problem, so this is how we have drawn the particular figure. So, here we have the outer tube, this is the inner tube, the liquid is flowing through this inner tube, the steam is coming through the outer tube, it is getting condensed as a function of at a given temperature, and this temperature may be a function of time, because the saturated temperature is a function of the pressure. So, depending on the pressure, if the pressure is varying, then this Ts will also vary. That is why the Ts has been shown to be a function of time. Okay, and now we are demarcating the two ends of the tube like Z equal to 0 and Z equal to L, and you can see the steam is condensing and we are getting the condensate over here. This is we are assuming it to be saturated liquid. Now we are assuming some things like that. We assume that the liquid is in plug flow. When it is plug flow, that means there is a good mixing in the radial direction. So there is only one velocity involved, and we call it a one-dimensional flow. And this flow is taken to be in the Z direction. Then we have the heat transfer in the axial flow is only by convection and conduction through within the liquid. As we say that in the liquid we are talking only of the convection, and the conductive heat transfer is neglected, and the steam temperature is taken to be constant. And as I said that the wall is not, this wall is not offering any resistance to the heat transfer, and we are assuming the liquid density, the liquid specific heat are remaining constant, and this particular assumption is not bad for the liquids, because you will find generally the within some reasonable temperature difference the properties of a liquid do not vary drastically. But in case of gases, this will not be the cases. In that case, you will have to generally take the variations of the properties with the pressure and the temperature. So here I have shown you the various notations I have used in this particular formulation, and I have also given you, for sake of your understanding, the SI units for these various notations. Why? Because whenever you are writing the balance equations, you should be very careful about the dimension on the two sides of the equations. And you know that if there is dimensional inconsistency, then you are having a wrong model equation, and wrong model equation will lead to wrong result. So I have put all these units to you so that you can check with these units whether you are getting dimensionally consistent energy balance or not. So here we have the balance equations. You can see the various variables which are involved in this particular system are: first is Z, that is the axial position. Now you see the Z is being varied between 0 and L without including the 0 and L. Why? Because we have been given the values of the temperatures at the inlet and the outlet. So we will be solving the energy balance equations only for the region within this 0 and L. Okay. Now this is, you can see that this is the situation when the boundary conditions are of type 1 or Dirichlet boundary condition. So if you have Neumann boundary condition, that means you do not know the outlet temperature, you may specify, say, the first derivative of the temperature with respect to the axial position to be 0. Okay, that means dou T by dou Z to be 0. That means you do not know the temperature at Z equal to L. In that case, you have to include that Z here and with L. So you will put less than equal to L. So for this particular problem, we are neglecting the calculation of the temperature at the position L. Then time is taken to be more than equal to 0. Now understand this, what we understand by time equal to 0. Time is not 0 actually. In any process, whenever we are analyzing it, we take the time to be 0 at the start of the process. Okay? So we are generally not concerned with the history of the process. Many times in some cases we have to know the history, but those cases are different. Like for example, in non-Newtonian flow and non-Newtonian fluid dynamics, sometimes we are also concerned with the history because the stress-strain relationship depends on the history of the particular fluid. But that is not the case here. So generally we take the time to be 0 for the starting time of the process, and we always march in future. So that is why we say that time is more than 0. Okay? And this is not the time of our watch. Okay? This is the time of the starting of the process. Okay? And then we have the TL, that is the liquid temperature, which is a function of the axial position and the time, and we have the wall temperature of the inner tube, that is the function of the axial position and the time. Now let us write the energy balance for the liquid and for the wall, and you can see that in the case of the liquid, you will find that this term is giving us the how much energy is being changed within the particular liquid. Okay, so this is the accumulation term. And then for the liquid we have the convective term. Okay, and convective term we are talking about only one dimensional flow, so we are having only one component of the velocity. And then we have we are neglecting the conductive heat transfer, so we do not have any conductive contribution over here, and what we have here now is a source term. This source term is coming due to the transfer of the heat from the wall to the liquid, and this term is taken in terms of the Newton's law of cooling, and that is why we are taking it HA delta T. And all these other AF and AI have been explained in the notation. This AF is the cross-sectional area of the inner tube. Okay. So, you can easily derive this particular equation for the liquid side energy balance, and then we come to the energy balance for the wall. Again we are having this term which is signifying that how the heat within the particular solid or the wall is changing. So, that is the accumulation term for the wall, and in case of wall we have neglected the convection heat transfer. So, we do not have the convective heat transfer term unlike the one we have in the case of liquid. Here we have, and as we said that we are also neglecting the heat transfer resistance due to the conduction in the solid. So, we do not have that term also, only what we have the source terms, and these source terms are coming. Why? One is because the heat is transferred from the steam to the wall. So, this is coming within the wall and this is going out of the wall, that is why it is negative sign. Okay. So, this is going from the wall to the liquid. Okay. So, you see these signs signify the direction of the flow of the heat. Okay. And that is how we are able to derive the energy balance equation for the wall. Now, you can see that with these two equations in hand, you see that they will give us the variation of the temperature of the tube of the wall and the liquid. And in these two equations you find that if I want to solve this equation for TL, I need the value of TW. But for knowing the value of TW, I have to solve this equation, but this can be solved for if I know the value of TL. So, what I find that we have two unknowns and these two unknowns are appearing in both the equations. So, we are having two coupled set of partial differential equations which have to be solved simultaneously to get the solution. Okay. But this is not the end of the situation, because we can solve it only if we know the initial condition and the boundary conditions for this particular system. So, I will be stopping at this, the derivation of this balance equation. In my next lecture, I will continue this problem to tell you how to specify the initial condition and the boundary conditions so that we can solve these equations. You can know more about this process from these references. Thank you.